Good morning, students. We'll continue the previous class. In that previous class, I was saying you about the simple microscope. Okay, now we are going to discuss about the compound microscope. What means this compound microscope? See here, if the magnification obtained by that simple microscope is not sufficient, I mean what? Okay, you taken one a small object and you weaved that one with the help of a simple microscope. I mean you taken one single magnifying lens and through that you observe that small object. Even at that time, if you were not going to get the clear and well magnified image of that small object, then we go with the help of that compound microscope. I mean, if that magnification by simple microscope is not sufficient, even there we can't able to see the clear image, then we go with the compound microscope. This is also an optical instrument which is going to produce the well magnified image of small objects. Well magnified image of small object. See, there is a main difference between simple microscope and compound microscope is that simple microscope is being with only one single biconvex lens. But here in this compound microscope, I mean this compound microscope is consisting two biconvex lenses. It being with two biconvex lenses. One we call as an objective lens and another one we call as an eye lens. See here, look on this diagram. Here this is the ray diagram of compound microscope. It is a very important diagram. Even here in your annual exam, they will be asking to draw the ray diagram of compound microscope. Then at that time, you have to draw this diagram. It will be carrying around 2 marks. Okay, look here. Look on this ray diagram. Here, this arrangement, I mean this compound microscope is being with two biconvex lenses. Here there is a one lens and here there is another lens. They are different in their size. This one has a small aperture, small focal length, and this one has higher aperture, I mean a greater aperture and greater focal length. Their sizes are different. So look here, the lens which has small aperture and small focal length is going to face the object. Mean what? That small lens is going to face the object means that small lens is near the object. That is going to be near the object. Here I mentioned AB as an object. A lens which is facing object means it is near to that object is called objective lens. A lens which is towards object called as objective lens. And there is one more lens, through that you will be seeing the image of the object, that you call as eye lens. A lens through which, see, this is arrangement like this, horizontally held. Your eye is here. You watching through this lens. You weaving through this. A lens through which you weave, you watch is called as eye lens. Have you understood? There are two lenses. A lens which is near to the object called as objective lens, and the lens through which you will be seeing the image is called as eye lens. Okay, so now you see here, now concentrate. Here AB is an object. AB is an object that placed in front of that objective lens. Here you should know some few things. Here O is the optical center of objective lens and E is the optical center point of eye lens. There are two lenses, so we have to represent them with O and E symbol. O for objective lens, E for eye lens. Okay. Then here I mentioned this point as capital FO. This one, capital FO. Subscript O is telling it is belonging to objective lens. Getting what I mean to say? What mean capital F? Capital F is the principal focus point. Principal focus point of objective lens. Okay, here this side also capital FO. I mean this is also principal focus point of objective lens. Similar, here I mentioned FE. This FE is the principal focus point of eye lens. Similarly this side. Okay, you should know. You represent them. Then only you can able to draw the ray diagram. It's a very important. Okay, already I said. Okay, this side F4 to F4 and O to F4 distances should remain same only. Okay, now concentrate. Now here that object AB is placed in front of that objective lens. Now in this compound microscope, actually here we want well magnified, I mean highly magnified image of the object. In this arrangement, AB is the object. Okay, yes. Now see here, that AB object is placed at a distance UO from that objective lens. U is the representation for object distance. Subscript O, I mean that is the object distance with respect to objective lens. Getting what I mean? In front of this objective lens, that object AB is at UO distance. Okay, AB is object for this objective lens. Okay, which is at distance UO. You have to represent them very clear. Okay, yes, fine. Now here I mentioned this one as FO, small FO. Small f is focal length. It is the distance between optical center and principal focus point. Okay, distance between these 2 points called as focal length. This is the focal length of objective lens. That's why I represented this as small f subscript O. Clear? Yes. Now you see, from this object we are going to take two light rays. One is, first of all, you should know one thing. Here in front of this objective lens, that object AB is held between FO and 2FO. I mean here 2FO point will come. Already we discussed 6 cases of biconvex lens. When object is held between FO and 2FO, then this side real inverted magnified image is going to form beyond 2FO. Okay, yes. Let just now you take 2 light rays from that object AB. One is a parallel light ray. This is a light ray which is parallel with respect to principal axis. This light, okay, here after getting refraction to that objective lens, here this light ray after getting refraction through this objective lens, it is passing through the principal focus of that lens. That already been, okay, yes. This light ray after refraction passed through that principal focus point. Fine, that is one. Take one more light ray. which is coming through the optical center, a light which is coming through or passing through optical center will not deviate. It will keep moving along its initial path only. I mean, it will keep moving straight only. Yes. These two refracted light ray got intersected here. This one and this one, they got intersected here. I mean, there they produce the image of that object AB. These two light rays came from the top portion of object AB. I mean, the image of this top portion of object is produced here. Okay, that image got produced here means this is which image? Real inverted image. It is inverted image. Fine. So now here there is a image formation. Now you see here. Okay. Here A dash, B dash, A dash, B dash is the image for objective lens. Okay. A dash, B dash is the image for objective lens. So that distance, see here I mentioned VO. V is the image distance. Some script O telling image distance for objective lens. Getting what I mean to say? For this lens, this is image. So this distance is VO. Here I mentioned. Okay, fine. Now A dash, B dash is the image for that lens. This A dash, B dash we taking as a object for eye lens. Here one more lens is there. In front of this eye lens, there is a dash, B dash, like this. Okay, it is inverted. This A dash, B dash we treating as the object for this lens. Object for this lens. Okay, see now, that's why I mentioned here the distance between this A dash, B dash and optical center E as a UE. UE, object distance for eye lens. Getting what I mean to say? See, listen. Here we doing some adjustment in that compound microscope. Okay. So right now that our ray diagram is along horizontal view. Suppose in your laboratory you will be using that compound microscope. You will be weaving it like along vertical line. You will be weaving it along vertical line. I mean, here there you will be having a eye lens, and here at the bottom there will be a objective lens. Below that you will be placing some specimen. I mean, you will be taking them as an object. Okay, you will be placing some specimen here. There is a lens called objective lens. Here one more lens is called as eye lens. Through this eye lens you will be watching like this. And there are some instruments, there are some adjustments. Some screws are there. With the help of those screws, you will be moving this eye lens up and down. You will be moving this eye lens. You will be moving this eye lens. For your one particular adjustment, while moving for one particular position of that eye lens, you will be getting a clear image. You will be getting clear image. Okay? Yes. What is that adjustment? You see here. What we doing here? Try to get it. Here, look here. A dash, B dash is the object for this eye lens. We want actually AB is object for instrument. That AB right now got enlarged. Okay, AB is this much. It is object actually. It got enlarged this much. This magnification which we got by that objective lens is not sufficient. Is not sufficient. Still we want it to enlarge. Still we need this A dash B dash in big size. Getting what I mean to say? That we are doing with the help of this eye lens. Okay, I mean still we need the enlarged view of A dash B dash. Getting what I mean to say? So now you see here A dash B dash is object for this one, that already we know. In front of any biconvex lens, if object comes between its principal focus point and optical center, then it is going to produce the virtual, erect, highly magnified image. Here we want magnified image, highly magnified we want. To get a highly magnified image by this eye lens, we have to take that object A dash B dash in between its principal focus and its optical center. Getting what I mean to say? To get highly enlarged image, we have to take that object between its principal focus and optical center. Getting what I mean to say? That adjustment, nothing but what we doing? We are trying to take the object in front of this eye lens between its optical center and principal focus point. Getting what I mean to say? Once object is going to come, see here, for this A dash B dash is object. Now you look here. FE is what? FE is the principal focus of this one. E is its optical center. Now you see here, this object is in between its optical center and principal focus. Then obviously this lens, biconvex lens, now is going to produce the virtual, erect, highly magnified image. Getting what I mean to say? Actually what we are doing here, doing like this means what? We taking that object, okay, in between principal focus point of eye lens and its optical center. You see here, principal focus is here, optical center is here. That object is lying between them. Okay? Yes, that we are doing here. Have you understood? Yes. Now look here. Once that object comes between principal focus and optical center, then you take two light rays to draw ray diagram. Look here. From this object A dash B dash, again I am taking two light rays. One is parallel light ray with respect to principal axis. A parallel light with respect to principal axis after refraction is going to pass through the principal focus point. Yes, this parallel light from that object after refraction passed through the principal focus. This light ray finally received by your eye. Okay? One more light ray from that object, this light ray, which is passing through the optical center. This light ray is passing through the optical center. It gone along its initial path only, because that is not going to change its path. This light ray, yes. These two light rays are refracted light rays. I mean, these two are the final light rays received by your eye. For your eye, these two light rays are looking diverging light rays. You see, these two are diverging. These two are diverging means here somewhere they are not going to meet. They are not going to converge. What that your eye will feel at that time? For your that eye, these two light rays are looking like diverging means that your eye will feel these two light rays came from somewhere. They diverging means as we feel they going back means they look like coming from a particular point. What I mean to say, you have to extend those diverging beams in backward direction. You have to extend those two diverging light rays in backward direction. You see here. This one I extended in backward direction, and this one also I extended in backward direction. Those two backward extended rays looking like coming from that intersection point. Okay, these two light rays looking like coming from that intersection point. Getting what I mean to? That your eye will feel the image at that point. For your eye, okay, these two light rays are giving the sense of presence of image at that point. So there, at that intersection point, there will be a final image. Which kind of image is this? For this eye lens. For this eye lens, that A double dash, B double dash is the virtual, erect, highly magnified image. For this, okay, object A dash, B dash was held vertically downward. Image also you got vertically downward. So it is virtual, erect, highly magnified image. Have you understood? For this eye lens, that A double dash, B double dash is the image. Here one adjustment we are doing. That image which we are going to get as a final, here in this compound microscope, we adjusting the position of that object in such a way that its virtual image should be formed at 25 cm from our eye. Getting what I mean to say? If it is formed within 25, then you can't able to see its clear image. That is the limit, least distance of distinct vision. Within 25 cm, our eye cannot able to see the objects clearly. That's why that forming image, at least it should be at 25 cm. That's why we adjusting here. We adjusting in microscope in such a way that that final image should be at a D point, should be at a near point. Have you understood? From your eye, that final image is at D point. Okay, this is about the ray diagram of compound microscope. Here you should know that very important. Here this distance is the image distance for that eye lens. Okay, so now here there are two magnifications. In this entire instrument there are two magnifications. First magnification is produced by objective lens. Object was AB. This lens enlarged that one. Okay, A dash, B dash is the image for that objective lens. I mean this objective lens here, it magnified that object. That magnified image of objective lens we considering as the object for eye lens, and further we going to enlarge it more. There are two magnifications. One is magnification by objective lens and another one is the magnification by eye lens. This combined magnification, this combined effect, this entire instrument we call as a compound microscope. Have you understood what means compound microscope? When we use this compound microscope means when the magnification produced by that one single biconvex lens is not looking sufficient, then further we going for more magnification, then we call it as a compound microscope. Okay, this is a very important. And one more thing you should know here the distance between objective lens and eye lens is called as the length of that microscope. From here to here, that I mentioned, that L is the length of the microscope. Have you understood? Yes. Now, here after having the idea about compound microscope, how it will work, Okay, now here we have to get the magnifying formula for this compound microscope. Okay, how we have seen for that simple microscope, similarly here also we are going to get the magnifying formula for this compound microscope according to first case and second case. Look here there is a first case I have written when the image, I mean that final image, when that final image is formed at near point. Near point means what? That is D point. Okay, look here, when that image is formed at near point, I mean at D point, then the magnifying formula of compound microscope, I already said in compound microscope there are two magnifications, one by objective lens and another by eye lens. Here the total magnification of this compound microscope is the product of magnification of objective lens and magnification of eye lens. To get a total magnification, we have to multiply those two individual magnifications. Okay, M is equal to MO into ME. MO means what? Magnification of objective lens into ME, magnification of eye lens. Look here, that already we know. Magnifying power of one single biconvex lens. Okay, in previous class only we discussed about that one. M is equal to that magnification, generally we defined as the ratio of height of the image to the height of object, or even we defined like that, that h dash by h we have taken as v by u, v by u. Okay, yes, in place of that MO I replaced it by VO by UO. This is the magnifying formula for one single biconvex lens. Okay, that I have written VO by UO. Okay, yes, see here. Then into ME, here I have written that in place of ME I have written as 1 plus D by FE. 1 plus D by FE. Why that I have written? Look here. For this eye lens, that image is formed at D point. Look on this single lens. Look on this single one. Okay, this single one is looking like simple microscope. One single biconvex lens is called as simple microscope. In previous class, we discussed the magnifying power of single lens, I mean magnifying power of simple microscope when final, I mean when image is produced at D point. That already we derived in previous class. That is 1 plus D by its focal length. That magnifying power of this simple microscope when final image is produced at D point is 1 plus that distance D by its focal length, that is FE. Okay, I mean its focal length, distance between these 2 points. Okay, that I have written here. 1 plus D by FE. Now look here, some small imagination is that here. If UO is equal to FO, UO is equal to FO means what? If UO, I mean object distance, is nothing but equal to focal length, means what? If suppose we have placed this object AB at a principal focus point, if we place that object AB at a principal focus point, then what will happen? In front of this one single biconvex lens, now that we are taking object at its principal focus point, then object distance will be its focal length. I mean what we imagining, if this AB is at this point, then object distance will become FO only, UO will become FO. In front of biconvex lens, when object is at its principal focus point, then that image is going to produce at. See here, when we take this object at this point, when object at its principal focus point, then obviously image will be at infinity. What we have to imagine here, when you take this here, this image is going to produce at infinity. Mean what? It's shifting here. This image A dash B dash going away. Maximum. See, you think like this. As it shifted at FO point, this A dash B dash is going away. Maximum possibility here. We have to treat then that VO. VO means what? Image distance. When object at principal focus, image is going to be at infinity. Actual. But in this arrangement, we maximum. If it is going away, then maximum that object, I mean that image distance we have to treat as length of that microscope. I mean what? This is going away to the infinite point. Okay, here that our instrument is going to end here. Maximum possible away movement is up to this point. Getting what I mean to say? When object came at principal focus point, this is going away. So maximum here in this case, we have to consider image distance as L only. I mean it is just imagination. If object condition it is. If object is at the principal focus point, then image, this image A dash B dash, image for objective lens is going to be at infinity. Okay, that we don't know. But we are going to treat that distance as L at that time. Okay, it is going away. I mean we are going to treat like that. Look here, that I have written. If UO is equal to FO, then VO, this image, going to be at infinity. Here in this instrument, that infinite distance we treat as L. Okay, that I have written here. Substitute them here. Okay, that M equal to VO by UO. VO is L by UO is FO into that as usual. This is the final formula for the magnification of compound microscope when image is formed at near point. When image is formed at D point, you have to remember this formula. Already I said you will be getting some numericals. There they will be telling you to calculate the magnifying power of that compound microscope when final image is formed at D point. At that time you have to use this formula. M is equal to L by FO. There L is the length of compound microscope. FO is the focal length of objective lens into 1 plus D by FE. D, that already you know its value. It is 25 centimeter. Okay. FE is the focal length of eye lens. Have you understood? They will give these all data and they will tell you to calculate magnifying power. I mean, you should know that equation. You should know that formula. Then only you can able to calculate that. Okay? Yes. Then second case. In that second case, when the image is formed at far point of eye is infinity. I mean at infinity. Look here. Then say what here we have to treat this final image should be at infinity. To get this final image at infinity, what we have to do? We have to do that arrangement here. We have to take this A dash B dash at the principal focus point of eye lens. When this A dash B dash will come here at the principal focus point, then image will be at infinity. For this eye lens, this is object. If you take this at its principal focus point by moving this one, just by moving this eye lens like this, if you you take that object at its principal focus point, then image will be at infinity. Getting what I mean to say? If this A dash B dash comes at this principal focus point, then that light ray, I mean these two refracted light rays are going to look like parallel. These two are looking like parallel. Okay, at that time your eye will feel these two parallel light rays came from infinite point. Getting what I mean to say? That we can. Okay, yes, suppose like that, if you have done, I mean if you got that final image at infinity, then what is the magnifying formula of this compound microscope? Again, it is the product of magnifying power of both lens, MO into ME. Again, MO is VO by UO into ME. For this eye lens, this is right now on single lens. It is a simple microscope. Okay, in front of this single lens, object is at its principal focus point, and image got produced at infinity. In previous class, in that simple microscope, we got that magnifying formula, magnifying power when image is formed at infinity as d by f, d by its focal length, d by its focal length, d by fe. Have you understood? Previously it was 1 plus d by fe. At that time image got produced at near point. When image is going to produce at far point, then it is d by fe. These two already have shown in previous class. Getting? Yes. Then again same analysis what we did. If that object for objective lens is at its principal focus point, then image is going to produce at infinity. Okay, then at that time image distance we treat as length of compound microscope. Then substitute these values over here, then you will get the magnifying power of compound microscope as a VO. See, in place of VO I placed L by FO into D by FE. Okay, this is the final magnifying magnifying formula for compound microscope when image is formed at infinity.